So this problem says a stone is thrown from a roof, just like the previous problem we worked where a shingle was thrown off of the roof of a building. We like to throw a lot of stuff off roofs in physics. The shingle, however, was thrown with the horizontal velocity. This stone is going to be thrown at some angle, so it has some initial velocity at some angle, theta sub I. And the question wants to know how long does it take the stone to reach the ground, and what is the speed of the stone just before it strikes the ground. So it's going to go all the way over here to the ending point. I'm going to take the origin to be on the ground underneath the launch point. That's how I usually do it. Your book takes the origin to be right here. It's fine, just as long as we set everything up and stay consistent. So, list out all of your kinematic variables. X initial, X final, Vx initial, Vx final, Ax, Tx. Y initial, Y final, Vy initial, Vy final, Ay, Ty, and then V initial and theta initial. Okay, so my initial velocity is given as 20 meters per second, and my angle of that launch is 30.0 degrees. So the height from which the stone is thrown is 45 meters above the ground. Well, if I put the origin at the ground, that means Y initial is 45 meters. Y final is 0 because it strikes the ground that time. X initial is also 0. And do we know anything about the range of this thing? No, we don't. Vx initial is equal to, remember, use our triangle here, cosine of theta sub I is equal to the adjacent Vxi over the hypotenuse Vi. So Vxi is equal to Vi cosine theta sub I. And the final is as well. The acceleration in the x direction is 0, and time equals, in the x equals time in the y, and we don't know what that is. The initial velocity in the y direction is Vi sine theta I, because sine of theta initial equals opposite Viy over Vi. And the final velocity, we don't know what that is. The acceleration is negative 9.8 meters per second squared because it's in free fall. So Ty equals Tx equals unknown. So this is one of these problems where we're going to have, we want to know how long does it take the stone to reach the ground. Find time. So if we knew the range, that would be easy because velocity times time equals distance, you know, that kind of thing. But we don't know that. We don't have enough information in the x dimension. So let's look in the y dimension. Y final minus y initial equals Viyt plus 1/2 Ayt squared. Alright, unfortunately this term doesn't equal 0. The final does, so I can say 0 equals 1/2 Ayt squared plus Viyt plus y initial. So if this term were 0, that would be a much easier situation, but it's not. If this term were 0, that would be an easier situation, but that's not the case either. So now we have a quadratic. We could solve for the final velocity first and then do a two-step deal, or we could just solve outright using the quadratic formula. Either way. There's one substitution I need to make. I need to put this in for Viy. So 0 equals 1/2 Ayt squared plus Vi sine theta I t plus y initial. Okay, so the solution, t equals negative b, where b is the b term of the quadratic. So negative Vi sine theta I plus or minus the square root of b squared, vi squared sine theta I squared, minus 4 times a, 1/2 ay, times c yi. Again, a, b, c are just the coefficients of the t second, t first, and t 0th term, all over 2a. I mean, you could simplify this a little bit if you want to. Vi sine theta I plus or minus vi squared sine squared theta I minus 2 ay y initial all over ay. Okay, so I'm gonna skip plugging in all the numbers. Let you do that yourself. What you end up with are two solutions of negative 2.18 seconds and t equals positive 4.22 seconds. Well, clearly only the positive solution is possible. So the next part of the problem says find the speed. Okay? So what that means is find the magnitude of the final velocity vector. Well, we have the final x velocity vector, so we need to find the final y velocity vector. So that's the first part. So vfy is equal to viy plus ayt. Vfy is equal to vi sine theta I plus ayt. And you can plug the numbers in there too. All right, I'll go ahead and do that. So v initial is 20 meters per second sine of 30 degrees plus negative 9.8 meters per second squared times 4.22 seconds. Vfy equals negative 31.4 meters per second, which makes sense because the final velocity in the y direction has to be downward. So Vfx equals, so this is the other thing, the Vfx, Vi cosine theta I, which equals 20 meters per second times cosine of 30 degrees. So Vfx equals 17.3 meters per second. Okay, so we have our two components. We have Vfx and Vfy. The way we find the speed, Vf is equal to the square root of Vfx squared plus Vfy squared. So Vf is equal to the square root of 31.4 meters per second squared plus 17.3 meters per second quantity squared equals 35.8 meters per second. That's the speed, which is the magnitude of the velocity at that point. Now the next part says write this velocity, not the speed, the velocity in unit vector notation. So this is a scalar, but we're going to write the vector Vf, which equals Vfx I hat plus Vfy j hat. So Vf equals 17.3 meters per second I hat minus 31.4 meters per second j hat. So the minus here is very important because remember this is a vector, so it has a magnitude and a direction.